The meat grinder. Imagine standing on a frozen railroad platform in the dead of winter. The kind of cold that turns your breath into fog before it even leaves your mouth. The kind of cold that makes metal crack and silence feel heavy. Then you hear it, not the rhythmic clatter of a normal train. Something else, something lower, something that vibrates through your boots before your ears can even process what is coming. You look down the tracks and what you see makes no sense. Racing towards you on rails, pushing through a wall of white, is something that looks less like a train and more like a weapon designed by the most ambitious supervillain who ever lived. A massive spinning wheel, taller than a house, wider than a room, churning through the snow like the world's most aggressive blender. Your brain tells you to run. Your legs do not move, and then it passes. And the snow that was piled 20 feet high on either side of the tracks simply disappears, blasted into a white explosion that hangs in the frozen air like a ghost before dissolving into nothing. That machine is called a rotary snowplow. And it exists for exactly one reason: destroying snow. Winter is one of the oldest enemies of the railroad industry. Before highways, before airports, before any of the transportation infrastructure we take for granted today, railroads were the circulatory system of entire nations. Goods moved by rail. People moved by rail. Mail, medicine, food, coal, everything that kept cities alive traveled on rails. And winter threatened all of it. A heavy snowstorm could bury tracks under drifts so deep and so dense that regular plows, the kind that push snow aside like a wedge, simply could not penetrate them. The snow was too heavy, too compacted, too deep. Trains would grind to a halt. Supply lines would freeze. Communities that depended on rail access for survival would be cut off. Engineers needed something more powerful, something that did not push snow aside, but instead ate it, and so the rotary snowplow was born. The concept behind the rotary snowplow is as brutal as it looks. At the front of the machine is a massive circular blade, a spinning wheel of steel teeth, arranged in a fan pattern. When the machine moves forward into a snowdrift, that wheel is already spinning at tremendous speed, and rather than meeting the snow with a flat face and trying to push it away, it meets it with 1,000 tiny impacts, each tooth biting into the drift and flinging the snow outward through curved channels that redirect it away from the tracks, sometimes launching it dozens of feet into the air. The result is that snowdrifts that would stop any conventional plow simply do not exist to a rotary snowplow. It does not negotiate with the snow. It does not compromise. It just destroys whatever is in front of it and keeps moving. What makes the rotary snowplow even more remarkable is just how old the technology is. Some of the rotary snowplows still used today are over 100 years old. Think about that for a moment. We are talking about machines built before the First World War. Machines that have outlasted entire generations of supposedly more modern equipment. Machines that were designed by engineers using slide rules and hand drawings, and yet are still considered irreplaceable in certain mountain railroad corridors. There is something deeply satisfying about that. In an age where technology becomes obsolete in 5 years, and phones are considered ancient after 2, a machine built in the early 1900s is still doing its job better than anything designed to replace it. But here is the detail that surprises almost everyone when they first learn it. Despite looking like the most powerful, unstoppable machine on rails, despite the spinning wheel of destruction at its front, and the clouds of snow it throws into the air, most rotary snowplows cannot actually move on their own. They have no engine driving their wheels forward. They rely entirely on locomotives pushing them from behind. So this terrifying machine, this railroad meat grinder that looks like it could chew through anything in its path, is essentially being shoved forward by another train, doing all the hard work of actually moving. The rotary plow provides the spinning destruction. The locomotive provides the muscle to push it into the drift. Together, they are one of the most effective winter maintenance machines ever invented. Separately, the rotary plow just sits there looking intimidating. There is a strange poetry in that. The most fearsome-looking machine on the railroad is also the most dependent. It cannot go anywhere without help. It cannot do anything without being pushed. And yet, when it is pushed, when it is sent into a wall of snow that would defeat anything else, it becomes something almost alive, something that chews and roars, and blasts and clears the way forward. Railroad workers who operate these machines describe them with a kind of reverence that is usually reserved for much more glamorous equipment, because they know something that tourists watching from a distance do not. When the worst storm of the decade comes howling down from the mountains and buries everything under 20 feet of ice and wind and white silence, the rotary snowplow is the only thing standing between the railroad and complete shutdown, and it has never let them down. Railroad-Omnibus noun. Imagine you are a traveler in rural Germany in the early 20th century. You have just arrived at a small country station after a long bus ride from your village. Your destination is the city, still hours away by train. You climb off the bus with your luggage. You wait on the platform, and then you climb onto the train. You settle in. You watch the countryside go by. And when the train reaches the next town, you have to get off again and find another bus to take you the last few miles to where you actually need to go. Every transfer costs you time. Every transfer costs you energy. Every transfer is another opportunity for something to go wrong, for a connection to be missed, for luggage to be lost, for a schedule to fall apart. Now imagine someone came to you and said they had solved this problem entirely. Imagine they told you that the bus you boarded in your village would simply continue onto the railway tracks without you ever having to move, carrying you all the way to the city in the same vehicle you started in. No transfers, no waiting, no lost connections. That is exactly what the Schienenzeppelin omnibus promised. And for a moment in history, it looked like it might actually change everything. The vehicle developed in Germany was one of the most ambitious transportation experiments of the 20th century. Engineers had long recognized that the biggest inefficiency in rural transport was not the speed of individual vehicles, but the dead time between them. The time spent waiting on platforms, the time spent transferring luggage, the time spent walking between connections. If you could eliminate the transfer entirely, you would not just save passengers a few minutes, you would transform the entire experience of traveling through rural regions. And the way to eliminate the transfer, engineers reasoned, was to build a vehicle that could operate on both roads and rails. The Schienenzeppelin omnibus was designed to function as a perfectly normal bus when driving on public roads, navigating village streets and country lanes just like any other vehicle of its era. But at certain specially equipped stations, something remarkable would happen. The bus would pull up to a rail connection point, retractable guidance equipment would deploy from beneath the vehicle, and it would gently roll onto the railway tracks. From that point forward, it would travel like a train, guided by the rails and traveling at rail speeds, until it reached another connection point, and returned to road mode to complete its journey through the streets of whatever city or town was its destination. On paper, this was elegant. This was brilliant. This was the kind of idea that makes perfect logical sense when you draw it on a whiteboard in a well-lit engineering office. The problem, as is so often the case with transportation innovation, was that the real world is not a whiteboard. The vehicle was expensive, not slightly expensive, prohibitively, crushingly, deal-breakingly expensive to maintain. Because it needed to perform well on both road and rail, it was essentially two vehicles worth of engineering packed into one body. Every system had to work in two different environments. Every component had to be robust enough for both road vibration and rail operation. The result was a mechanical complexity that made maintenance a nightmare and costs spiral beyond what any regional transport operator could sustain. Beyond cost, the concept required specialized infrastructure at every connection point. You could not just drive a Schienenzeppelin omnibus onto any section of track. You needed specific transfer stations, specific guidance systems, specific trackside equipment. Every town that wanted to be served by the system needed investment before the system could even reach it. And as transportation evolved, as roads improved, and conventional bus networks expanded, the advantages that the omnibus had promised began to look smaller and smaller compared to the complexity and expense it demanded. The world moved on, the concept faded, and today, the Schienenzeppelin omnibus exists only in engineering history books, and the imaginations of people who wonder what public transport might look like if that one strange experiment had somehow found the funding it needed to grow. Hamster wheel train. There are mountains in the world that are not meant to be climbed by machines. Mountains so steep that the very idea of running a passenger railway up their slopes sounds like the kind of thing an overconfident engineer says before someone reminds them of gravity. And then there are the engineers who hear that skepticism and go build the railway anyway. The Stoosbahn in Switzerland is one of those railways. It is not merely steep, it is the steepest passenger railway on Earth. At its maximum gradient, the track climbs at 110%. If you have never thought about what that means, take a moment to really picture it. At a 100% gradient, for every meter you travel horizontally, you also rise 1 meter vertically. You are essentially climbing at a 45-degree angle. The Stoosbahn exceeds even that. You are climbing at a slope so extreme that in a conventional train car, passengers at one end of the carriage would be significantly higher than passengers at the other end, and everyone would be gripping their seats and trying not to slide into the person behind them. This was the engineering problem that the designers of the Stoosbahn had to solve. You cannot simply build a normal train and point it up a mountain this steep. The physics do not allow for a comfortable passenger experience, and a comfortable passenger experience was non-negotiable because this was not a freight line or a maintenance track. This was a railway that needed to carry thousands of ordinary people safely and comfortably up to a mountain village every single day of the year. The solution they came up with was so unusual, so visually strange, that photographs of it still make people stop and look twice before they believe what they are seeing. The trains of the Stoosbahn are built with rotating barrel-shaped cabins. The cabins themselves are cylindrical in form, and they are mounted on the train's chassis in a way that allows them to rotate as the angle of the track changes. As the train begins to climb and the gradient increases, the cabins slowly rotate to compensate, keeping their floors level relative to the ground, even as the track beneath them tilts to an almost impossible angle. Passengers sitting inside experience something close to normal. The floor beneath their feet stays flat. The seats remain upright. The windows show the mountain rushing past at a dramatic angle, but the interior of the cabin itself feels surprisingly ordinary. You could be on a gentle commuter train in a flat city, except that outside the windows, the landscape is doing something that landscapes should not be able to do. From the outside, watching the Stoosbahn climb its mountain, the effect is genuinely surreal. The train moves up the slope, and the cabins rotate, and the whole thing looks less like a railway vehicle and more like some enormous mechanical creature crawling up the face of a cliff, its segments adjusting and adapting as it goes. Rail fans who have filmed it describe the experience of watching it as something between hypnotic and deeply unsettling. It looks wrong. It looks like something that should not work. And yet it works perfectly, carrying thousands of passengers safely up one of the most extreme railway gradients on the planet every single year. Its rotating hamster wheel cabins, turning the impossible angle of that mountain into just another comfortable journey up to the village above the clouds. Jet train. There is a category of engineering experiment that can only be described as a magnificent act of stubbornness. These are the projects where someone looks at a perfectly functional machine and says, what happens if I attach aircraft engines to it, and then actually does it, and somehow gets it to work? The M497 Black Beetle is perhaps the finest example of this particular tradition in the history of American railroading, and the story of how it came to exist tells you everything you need to know about the engineering culture of the 1960s, which was a culture that genuinely believed the answer to almost any question involving speed was to add more power and see what happened next. By 1966, the New York Central Railroad was facing a problem that many American railroads were starting to confront: speed. Not the speed of their existing trains, which was adequate, but the speed that passengers were beginning to expect. Aviation was growing. The interstate highway system was expanding. If railroads wanted to compete for passengers on medium-distance routes, they needed to demonstrate that trains could go faster, much faster. But rebuilding entire rail networks for high-speed operation was enormously expensive and would take decades. Engineers needed a way to test the limits of what steel wheels on steel rails could actually do without first spending billions of dollars on new infrastructure. The solution that engineers proposed was extraordinary in its simplicity and slightly alarming in its execution. They took a standard Bud rail diesel car, a perfectly ordinary piece of railroad equipment that had been running passenger services for years, and they attached two General Electric J47 jet engines to the roof of it. These were not scaled-down or modified jet engines. These were the same engines used on military aircraft. They were bolted to the top of the rail car with the exhaust pointing backward, and the resulting machine was given the name M497. But the engineers who worked on it called it something else. They called it the Black Beetle. On a straight section of track in Ohio, the Black Beetle was tested under carefully controlled conditions. Engineers wanted to see exactly how fast a conventional rail vehicle could travel on existing track before the physics became unmanageable. What they found exceeded almost every expectation. The Black Beetle reached speeds of over 180 miles per hour. For 1966, on conventional track, with steel wheels, this was a number that genuinely shocked the railroad engineering community. It proved something that many had doubted, which was that the limiting factor in American rail speed was not the fundamental technology of steel wheels on steel rails, but rather the condition and geometry of the tracks themselves. The Black Beetle never carried passengers. It was never intended to. It was a data-gathering exercise, a rolling laboratory designed to push the boundaries of what was possible and report back. And in that role, it was a remarkable success. The data it generated contributed to subsequent research into high-speed rail in America, even if the specific method of strapping jet engines to a commuter rail car was never seriously proposed for public service. Today, the M497 Black Beetle is remembered as one of the most audacious experiments in American railroad history, proof that sometimes the most valuable engineering breakthroughs come not from careful incremental progress, but from someone deciding to bolt jet engines to a train and see what happens. Railplane. Every era of transportation history has its great what-if stories. The machines and systems that came so close to changing everything, that demonstrated they could work, that attracted serious attention from serious people, and then somehow failed to make the leap from promising experiment to world-changing reality. The Bennie Railplane is one of those stories, and it is one of the most fascinating, because it did not fail because it did not work. It failed for reasons that had nothing to do with engineering, and everything to do with money, and timing, and the particular cruelty of history. George Bennie was a Scottish engineer who looked at the transportation landscape of the 1930s and identified a genuine problem. Railways were the backbone of long-distance travel, but they were getting crowded. Freight trains and passenger trains shared the same tracks, and freight trains were slow, which meant passenger trains got stuck behind them and could not run at the speeds that the technology of the era could theoretically achieve. The solution, Bennie reasoned, was separation. Give passenger travel its own dedicated pathway through the air, elevated above the existing rail network, and passenger vehicles could travel at whatever speed they were capable of without ever being held up by a slow-moving coal train on the tracks below. The Bennie Railplane system was designed around this insight. Passenger cabins would hang from an elevated overhead rail structure, suspended rather than sitting on tracks, which allowed for a smoother ride and a sleeker aerodynamic profile. And to propel these suspended cabins, Bennie chose propellers, aircraft-style propulsion mounted on the vehicles themselves, which gave the whole system an appearance that was genuinely unlike anything else on rails at the time. It looked like someone had crossed a railway with an airship and somehow made it work on a fixed track. In 1930, Bennie constructed a test line near Glasgow, a short but fully functional demonstration track that allowed him to prove the concept in front of investors, officials, and members of the public. The system worked. The railplane moved. It was smooth and fast, and generated genuine excitement among the people who saw it demonstrated. Newspapers covered it. Engineers studied it. For a brief period, it seemed entirely possible that elevated propeller-driven passenger railways might become a fixture of the modern transportation landscape. But the 1930s were a brutal decade for ambitious infrastructure projects. The global economy had collapsed. Investment capital had vanished. The kind of large-scale commitment needed to build an elevated rail network across an entire country was simply not available, not from private investors who had lost fortunes in the crash, and not from governments that were dealing with unemployment and social crisis on a scale that made experimental transportation systems a very low priority. Bennie spent years trying to find funding, trying to keep interest alive, trying to convince the people who had the money that his system was worth building. He never succeeded. The test line near Glasgow was eventually demolished. The railplane never ran again. And George Bennie died, having watched his working, proven, genuinely innovative transportation system disappear without ever becoming what it should have been. Monorail in 1907. An inventor walked into a demonstration and showed the world a train that appeared to be breaking the laws of physics. Not appearing to break them in a vague metaphorical sense, but in the very specific and viscerally unsettling sense of a fully loaded passenger vehicle balancing on a single rail, moving through curves, stopping, starting, and remaining perfectly upright throughout all of it, without any visible means of support on either side. The audience that watched Louis Brennan demonstrate his gyroscopic monorail did not know whether to applaud or run. What they were seeing looked impossible. What they were seeing was, in fact, one of the most elegant pieces of mechanical engineering of the early 20th century. The fundamental problem with any monorail is the same problem you face when you try to balance a pencil on its tip. Gravity wants to pull it to one side or the other, and without something to catch it, it falls. Traditional railways solve this by having two rails, one on each side, so the weight of the train is spread between them, and falling in either direction is prevented by the rail on that side. A monorail eliminates one of those rails, which means the train has to somehow maintain its own balance without any lateral support. This sounds like an engineering problem with no solution. Louis Brennan found a solution anyway. Hidden inside the body of Brennan's monorail were two large gyroscopes, spinning at thousands of revolutions per minute. A gyroscope is a spinning wheel mounted in such a way that it can rotate freely in any direction, and a spinning gyroscope has a remarkable property called gyroscopic rigidity, which means it strongly resists any attempt to change the direction of its spin axis. Think of a spinning top. While it is spinning fast, it stays upright, because any force that tries to tilt it is met with a counterforce that pushes it back. The moment it slows down, it loses that resistance and falls over. Brennan's gyroscopes were the spinning tops inside his monorail, providing the force that kept it upright even when carrying a full load of passengers through a curve at speed. The reason Brennan used two gyroscopes rather than one was equally clever. A single large gyroscope, while providing stability, would also create a tendency for the vehicle to want to lean in a particular direction when it went around curves, which would make the ride uncomfortable and potentially dangerous. By using two gyroscopes spinning in opposite directions, Brennan ensured that their side effects canceled each other out, while their stabilizing effects combined. The result was a monorail that was genuinely, provably stable under real operating conditions, not just in theory, but in front of crowds of astonished observers who could see with their own eyes that this single-railed vehicle was not going to fall over. Crowds were amazed. Officials were intrigued. Some of the transportation experts who saw the demonstration genuinely believed they were looking at the future of urban mass transit. A single rail system would be cheaper to build than a double rail system. It would take up less space. It would be quieter and smoother. If the gyroscopic stabilization technology could be made reliable and affordable at scale, the Brennan Monorail offered real advantages over conventional railways. But that was the critical question. Could the technology be made reliable and affordable at scale? The gyroscopes required constant power to keep spinning. If the power failed, the stability failed, and a loaded passenger car balanced on a single rail would fall over. The mechanical complexity of the system was significant, and the cost of manufacturing gyroscopes capable of running reliably for the thousands of hours required in daily rail service was beyond what the economics of the era could support. Traditional railways, with their simple and robust twin-rail geometry, won the competition. The Brennan Monorail was retired, and one of the most brilliant pieces of mechanical engineering of its century became a historical curiosity rather than a transportation revolution. Train Zeppelin speed has always been the obsession at the heart of railroad engineering. From the very beginning, from the moment the first steam locomotive demonstrated that a machine could move faster than a horse, engineers have been asking the same question over and over again. How fast can we go? Every decade brings new answers, new records, new machines designed specifically to push the boundary of what is possible on rails. But few of those machines have been quite as strange, quite as single-mindedly focused on pure speed at the expense of everything else, as the Schienenzeppelin of 1931. It was a machine that seemed to have been built for the sole purpose of going very fast and being absolutely useless for anything else whatsoever. Franz Kruckenberg was a German engineer with a deep and serious interest in aerodynamics and a correspondingly deep frustration with the weight and drag of conventional railway vehicles. Traditional trains were heavy. They had to be heavy to carry freight and passengers and all the structural equipment needed to make them safe and reliable. But all that weight was the enemy of speed. Every kilogram you added to a train was a kilogram that the engine had to work harder to accelerate, and a kilogram that created more resistance against the air. Kruckenberg wanted to strip all of that away and build the lightest, most aerodynamically efficient rail vehicle that technology of the era could produce. The result was the Schienenzeppelin. It was long and narrow and shaped with an almost obsessive attention to aerodynamics. Its body tapering at both ends to reduce air resistance to the minimum achievable with the engineering tools of the 1930s. It weighed almost nothing compared to conventional railway vehicles of similar length, and instead of a traditional locomotive engine driving wheels against the rails, it used an aircraft engine, mounted at the rear of the vehicle, driving a large pusher propeller. The propeller spun and pushed air backward, and the Schienenzeppelin moved forward, exactly like an aircraft on a runway, except that it stayed on the runway, guided by the rails, and the runway never ended. On the 2nd of June 1931, on a section of track between Hamburg and Berlin, the Schienenzeppelin set a rail speed record of 230 kilometers per hour. This was not a marginal improvement over existing records. This was a number that left conventional railway thinking behind entirely, a speed that most people at the time would have considered impossible for a land vehicle of any kind, let alone one running on rails. Engineers across Europe took notice. The record stood for years, and the Schienenzeppelin became one of the most famous experimental vehicles in railroad history. But the problems were obvious to anyone who thought about the machine for more than a few minutes. A vehicle propelled by a rear-mounted pusher propeller is extraordinarily dangerous in any situation where another vehicle or a person might be on or near the track behind it. The propeller was exposed. It was enormous. It was spinning at tremendous speed. The idea of operating such a vehicle in any real-world rail environment where level crossings existed and maintenance workers walked the tracks and other trains shared the infrastructure was essentially unworkable. Beyond safety, the Schienenzeppelin had no practical capacity. It could carry a small number of passengers and nothing else. There was no room for freight, no room for mail, no room for the cargo that made railways economically viable. It was a speed machine and nothing else, brilliant at its one purpose and completely incapable of anything beyond it. The world eventually moved on to other approaches to rail speed, but the Schienenzeppelin remains, in the memory of railroad history, the most spectacular one-trick vehicle ever put on rails. Rail truck. Not every great story in railroad history is about speed records or revolutionary engineering concepts. Some of the best stories are about survival, about a railroad that was running out of money and running out of options and found a solution so simple and so practical and so far outside the normal thinking of the industry that it ended up being more enduring than anything the big railroads with their vast resources and their teams of professional engineers ever produced. The story of the Galloping Goose is a story about what happens when necessity meets ingenuity, and neither of them has any money to spend. The Rio Grande Southern Railroad ran through the mountains of Colorado in some of the most beautiful and most logistically challenging terrain in the American West. The mountains that made the scenery spectacular also made the railroad expensive. Running full-size steam locomotives through high-altitude passes, maintaining track through terrain that froze solid in winter and washed out in spring, hauling coal and water to remote engine facilities. All of it cost money that the Rio Grande Southern increasingly did not have. By the 1930s, the railroad was in serious financial trouble, and the management faced a choice that railroads in difficulty have always faced: find a way to cut costs dramatically or shut down. The solution they developed was genuinely creative. Instead of running full-size trains to carry passengers and mail and small freight loads on routes where the traffic did not justify the expense, they built a series of lightweight rail vehicles using automobile and bus technology. These vehicles were assembled from available parts, trucks and bus bodies, and whatever mechanical components could be sourced cheaply, and they were fitted with flanged wheels that allowed them to run on the existing railroad tracks. They were not elegant. They were not beautiful in any conventional sense. They looked, to put it plainly, bizarre, like someone had taken a bus and a truck and a railroad car and put them all in a bag and shaken it until something fell out. Someone looked at them running down the tracks with their ungainly proportions and their improvised appearance and gave them a name that stuck forever: the Galloping Goose. 7 galloping geese were built in total, each one slightly different from the others, as the railroad's mechanical staff learned what worked and what could be improved. Number 7 was the last and the most refined, built in 1936, and representing the accumulated knowledge of everything the railroad had learned from building and operating its predecessors. It carried passengers, it carried mail, it carried small freight, it did the work of a full-size train at a fraction of the cost, consuming far less fuel, requiring far less maintenance, and needing only a single operator rather than the full crew required for a steam locomotive. While the great steam locomotives of the era got all the attention and all the glory, Galloping Goose No. 7 quietly went about the business of keeping a struggling mountain railroad alive through some of its hardest years. The Galloping Goose served the Rio Grande Southern until the railroad finally closed in 1952. Several of the original vehicles survived and can be seen today in museums and on preserved railways in Colorado. They are beloved by rail enthusiasts, not for their power or their speed or their technical sophistication, but for what they represent, which is the determination to keep a railroad running by any means necessary, to find a practical solution when no elegant solution was available, and to do the work that needed doing, regardless of how strange the machine doing it happened to look. Aerotrain, and then there are the failures that hurt more than the successes. The projects that arrived with so much promise, so much investment, so much genuine belief that they were going to change everything, and then collapsed so completely and so publicly that they became cautionary tales rather than triumphs. The General Motors Aerotrain is that kind of story. It is the story of a machine that tried to save American passenger rail and instead became one of the most famous embarrassments in the history of the industry. By 1955, American passenger railroads were in trouble. The automobile had arrived in force, and millions of Americans who had previously traveled by train were now driving to their destinations on the new interstate highways being built across the country. Commercial aviation was growing, and the airlines were beginning to compete seriously for longer-distance passengers. The railroads needed to modernize. They needed to offer passengers something that cars and airplanes could not, which meant comfort, speed, and a travel experience that felt genuinely modern, rather than like a holdover from an earlier era. General Motors, which had significant interests in the railroad supply industry, believed it had the answer. The Aerotrain was designed to look like the future. Its exterior was sleek and streamlined, with a low profile and a visual language borrowed directly from the jet age aesthetic that was dominating American design in the mid-1950s. It was built using bus-style passenger cars rather than traditional heavy rail coaches, which dramatically reduced the weight and therefore the cost of manufacture and operation. The engineering logic was straightforward. Lighter train means less fuel. Less fuel means lower operating costs. Lower operating costs means the railroad can offer cheaper tickets. Cheaper tickets means more passengers. More passengers means a viable business. On paper, it was a compelling argument. General Motors was confident. The railroads that agreed to test the Aerotrain were hopeful. And then the train went into service, and passengers discovered what the designers had apparently not considered carefully enough, which was that a lightweight bus body, attached to conventional rail running gear, on existing American track, does not produce a comfortable ride. It produces a nightmare. The problem was physics, and it was brutally simple. Traditional heavy rail coaches worked well on the imperfect tracks of the American rail network because their weight provided inertia that smoothed out the bumps and irregularities in the track. The lightweight Aerotrain had no such inertia. Every imperfection in the track translated directly into movement felt by passengers. Every joint between rail sections sent a jolt through the car. Every curve felt exaggerated. Every slight deviation in the track geometry produced a sway or a bounce that in a heavier car would have been absorbed and dampened, but in the Aerotrain was transmitted directly to the seats and the bodies of the people sitting in them. Passengers described the experience as riding in a shopping cart, being pushed down a bumpy road. They described it as noisy. They described it as exhausting on longer journeys. They did not care that it looked modern. They cared that it was uncomfortable. And uncomfortable passengers are passengers who find alternative transportation. The railroads that had invested in the Aerotrain quickly discovered that its operating costs were not delivering the savings that had been promised either. The bus engines used to power it were not designed for the continuous high-duty cycle of rail operation and required frequent maintenance. The lightweight construction that was supposed to reduce costs was creating other expenses. The promised advantages were not materializing. Within a few years of entering service, the Aerotrain was being quietly withdrawn from the main lines where it had been expected to shine and reassigned to secondary routes where passenger expectations were lower. Eventually, it disappeared from service entirely, leaving behind a small number of vehicles and a very large lesson. The lesson was one that the railroad industry, and the transportation industry more broadly, has had to learn over and over again across its history. Technology that looks modern is not the same as technology that works. A beautiful exterior is not a substitute for a comfortable ride, and passengers, who are ultimately the reason any passenger railroad exists, will choose comfort and reliability over novelty every single time. The Aerotrain tried to save American passenger rail by making it look like the future. What it actually needed was to make it feel better than the present. It failed to do that, and it paid the price that all transportation ventures pay when they forget who they are supposed to serve. The Aerotrain is remembered today not as the machine that revived American passenger rail, but as the machine that tried and failed so spectacularly that it became a warning to every engineer and every executive who came after it. Sometimes the strangest lesson in railroad history is not the one taught by the most exotic machine. Sometimes it is the one taught by the machine that looked the most normal and turned out to be the most misguided of them all.